Fagioli, an industry leader in heavy lifting and transport, once again demonstrated their expertise with the successful loading of two 950-ton reactors in Venice using the Liebherr LR 11350 crawler crane. This operation stands as a testament to Fagioli's commitment to precision, safety, and efficiency in handling some of the largest and most complex industrial components in the energy sector. The reactors, enormous in size and weight, required careful planning and exceptional technical skill to be transferred from their assembly location to a barge for transportation to their final destination. The unique environmental and logistical challenges of Venice added to the complexity of the operation, making it one of Fagioli's standout projects in recent years. The challenge of lifting 950-ton reactors. The reactors, which are essential components in energy production, weighed a staggering 950 tons each. These reactors are designed to withstand immense pressures and temperatures during operation, making their construction both robust and incredible. Moving such components requires specialized equipment and a highly skilled team to manage the operation safely and efficiently. The task was to move these reactors from the fabrication site in Venice onto a barge for their subsequent journey, likely toward an industrial or energy facility. The choice of Venice as the location for this operation presented its own set of challenges. Known for its canals, narrow spaces, and historical significance, Venice is not typically associated with heavy industry or large-scale lifting operations. Transporting and lifting such massive components in this unique setting required not only technical expertise, but also careful consideration of the surrounding environment. The operation had to be meticulously planned to ensure that the city's infrastructure and natural waterways were not affected during the lifting process. Selecting the Liebherr LR 11350 crawler crane. Given the immense size and weight of the reactors, Fagioli selected the Liebherr LR 11350 crawler crane, a machine known for its outstanding lifting capacity and versatility in handling extremely heavy loads. The LR 11350 is one of the largest and most powerful crawler cranes in the world, with a maximum lifting capacity of 1,350 tons. It is equipped with a lattice boom that can be extended to great lengths, allowing it to handle tall or oversized components with ease. Additionally, the crane is designed to operate in a variety of environments, from industrial sites to more constrained or sensitive areas such as Venice. The decision to use the LR 11350 was crucial in ensuring the success of the operation. Its advanced hydraulic systems, coupled with its robust design, meant that the crane could lift and maneuver the reactors with precision. Despite their immense size, this crane's ability to handle heavy loads with such control was essential for an operation in Venice, where space is limited, and any misalignment could have had significant consequences. Fagioli's team knew that only a crane of this magnitude and capability could complete the job safely and efficiently. Pre-lift planning and engineering expertise. Before the reactors could be moved, Fagioli's engineering team undertook extensive pre-lift planning to ensure that every aspect of the operation was accounted for. This stage of the project involved detailed assessments of the load distribution, crane positioning, and environmental factors, such as weather conditions and tides. Venice's unique location, with its waterways and frequent tide changes, required additional considerations to ensure that the lift could be performed without any disruption to the city or its infrastructure. One of the key aspects of the planning process was calculating the reactor's center of gravity. Given the immense size of these components, it was critical that the load be evenly distributed to avoid any tipping or structural stress during the lift. Fagioli's engineers used advanced software and simulation tools to determine the optimal rigging configuration for the reactors, ensuring that the lifting process would be smooth and controlled. The team also had to consider the positioning of the LR 11350 crane. Given the limited space available in Venice, careful thought went into selecting the exact location for the crane to ensure that it could perform the lift without any obstructions. The crane's placement had to allow for the full extension of the lattice boom, while also providing enough clearance for the reactors to be moved safely onto the barge. This level of planning and attention to detail is what sets Fagioli apart in the heavy lifting and transport industry. The lifting process. Once the planning and calculations were complete, the actual lifting operation began. The reactors were rigged using specialized lifting frames and heavy-duty slings, which were carefully attached to the reactors at predetermined lifting points. These slings and frames were designed to distribute the weight evenly across the reactor, ensuring that there was no excessive stress on any part of the structure during the lift. The LR 11350 crane, with its impressive lifting capacity, slowly and steadily lifted the first 950-ton reactor off the ground. Throughout the lift, the Fagioli team monitored the operation closely, using real-time data from sensors to ensure that the load remained balanced and stable. The hydraulic systems in the LR 11350 allowed for fine adjustments to be made during the lift, ensuring that the reactor could be moved with incredible precision. This level of control was critical, especially given the confined space in which the crane was operating. As the reactor was lifted into the air, the crane's lattice boom extended to position the component over the waiting barge. The slow, deliberate movements of the crane ensured that the reactor was placed onto the barge without any sudden shifts or instability. Once the first reactor was secured on the barge, the process was repeated for the second reactor. Fagioli successfully executed the roll-up of a 650-ton jacket section in Ravenna, Italy. The jacket, a crucial structural component used in offshore platforms for the oil and gas industry, required careful handling to rotate it from a horizontal to a vertical position. This roll-up process was an essential step before the jacket could be transported and installed offshore. Given the structure's immense weight and the complexity of the task, the operation required advanced equipment, meticulous planning, and expert execution. The jacket's roll-up operation involved lifting the structure from its fabrication position in a horizontal orientation and rotating it to the vertical position required for transport and installation. The 650-ton weight posed a significant challenge, but Fagioli's engineering team was well prepared, drawing on their vast experience and technical expertise to ensure the operation was carried out safely and efficiently. The company used state-of-the-art equipment, including strand jacks and cranes, to lift and rotate the massive structure. Strand jacks, in particular, were crucial for the precision lifting required in the operation. These hydraulic lifting devices work by using steel cables to slowly raise or lower heavy loads, allowing for precise control during the lifting process. In the case of the jacket roll-up, the strand jacks were attached to the structure at carefully selected lifting points to ensure even weight distribution and prevent structural stress during the rotation. Before the lift, Fagioli's engineers conducted detailed assessments and planning to determine the structure's center of gravity, the appropriate lifting points, and the forces that would be applied during the roll-up. This planning also considered the environmental conditions in Ravenna. such as wind speed and ground stability, to ensure the operation was carried out in the safest conditions possible. Safety was a top priority, and Fagioli's team meticulously monitored every aspect of the operation, adjusting the process in real time based on data from sensors and control systems. The actual roll-up process was slow and methodical. The jacket was gradually lifted and rotated, with strand jacks performing fine adjustments to maintain balance and control. Cranes provided additional support during the final stages of the roll-up, ensuring that the jacket reached its vertical position smoothly and without incident. The combination of strand jacks and cranes, along with the expert coordination of Fagioli's team, allowed the 650-ton structure to be rotated safely and efficiently. Upon completion, the jacket was secured in its vertical position, ready for transportation to its offshore installation site. This successful roll-up operation demonstrated Fagioli's ability to manage complex heavy lifting projects with precision and care. Their use of advanced technology, detailed engineering planning, and highly skilled personnel ensured that the project was completed without any safety issues or delays. This operation not only reinforced Fagioli's reputation as a leader in the heavy lifting and transport industry, but also highlighted their ability to handle challenging projects in the offshore oil and gas sector. Fagioli, a global leader in heavy lifting and transport, successfully completed the load out of a massive 6,600-ton offshore jacket using their advanced skid shoes technology. This offshore jacket, a crucial structural component in the oil and gas industry, required a high level of precision and expertise due to its colossal size and weight. The loadout involved carefully moving the jacket from the fabrication yard onto a barge, where it would later be transported to its final offshore installation site. Given the sheer scale of the jacket, the operation demanded not only technical skill, but also a reliable method to ensure safe handling throughout the process. At the heart of this operation was Fagioli's use of skid shoes, a specialized tool designed for the controlled movement of large, heavy objects over short distances. Skid shoes work by utilizing hydraulic systems that slightly lift the load off the ground, enabling it to slide along steel tracks. This method distributes the structure's weight evenly across the shoes, significantly reducing friction and minimizing the risk of structural stress. For the 6,600-ton jacket, the weight was carefully transferred onto multiple skid shoes positioned at key load-bearing points, ensuring stability throughout the maneuver. The size and complexity of the jacket meant that precise coordination and meticulous planning were essential. Fagioli's engineering team undertook extensive calculations to determine the jacket's center of gravity and developed a loadout strategy that would guarantee safe and efficient movement. The hydraulic jacks within the skid shoes enabled fine adjustments to the jacket's position, allowing for controlled movement and preventing any misalignment that could cause damage. This high level of control was critical in ensuring the safety and success of the operation. Throughout the loadout, Fagioli's team monitored the process in real time, making adjustments as necessary to ensure a smooth execution. The successful use of skid shoes in this project underscores Fagioli's expertise in managing complex and oversized structures, highlighting their commitment to delivering innovative, safe, and efficient solutions in challenging industrial environments. The lifting and installation of two 2,000-ton slurry reactors in chemical processing plants, particularly in industries such as petrochemicals, oil and gas, and fertilizer production, is a remarkable feat of engineering and project management. Slurry reactors, given their critical role in processing raw materials into valuable end products, must be handled with utmost care and precision. They are essential in processes such as Fischer-Tropsch synthesis for converting natural gas or coal into liquid fuels, in the production of synthetic chemicals and fertilizers, and in other large-scale chemical reactions where the handling of solid particles within a liquid phase is required. These reactors must withstand extreme operational conditions, such as high temperatures and pressures, making their safe transport, lifting and installation vital for ensuring plant productivity and safety. The process of setting up these reactors can be broken down into several phases: detailed planning, preparation of lifting equipment, execution of the lift, installation of the reactors on their foundations, and integration with the plant's operating systems. Each step is meticulously planned and executed, with no room for error, considering the size, complexity, and criticality of these reactors in the chemical production process. The first and arguably the most crucial phase of the project is the planning stage. This is where all necessary preparations are made, designs are finalized, risks are assessed, and resources are allocated. For lifting slurry reactors of this scale, a comprehensive and detailed plan must be established to ensure that every step of the operation is executed seamlessly and safely. The installation site must be thoroughly analyzed to assess its capacity to handle the weight and stress imposed by both the heavy lifting cranes and the reactors themselves. This involves a detailed geotechnical survey of the ground to ensure its load-bearing capacity is sufficient. If the soil or foundation is deemed insufficient to support the weight of the cranes and reactors, ground reinforcement measures are implemented. This may include compacting the soil, installing load-spreading mats, or constructing concrete pads for the cranes to rest on. Without proper ground preparation, there is a risk of ground settlement during the lift, which could lead to disastrous results. Environmental factors are a significant concern during the planning phase. Weather conditions such as wind speed, temperature, and precipitation can have a direct impact on the safety and success of the lift. Wind, in particular, poses a substantial risk when lifting large and heavy objects, as it can cause the load to sway, putting additional stress on the cranes and rigging. For this reason, the lift must be scheduled during favorable weather conditions, with continuous monitoring to ensure that any sudden changes are accounted for. Safety is a paramount concern at every stage. Detailed risk assessments are conducted to identify potential hazards and develop mitigation strategies. This includes determining escape routes, securing the lifting area from unauthorized personnel, and preparing contingency plans for unforeseen events, such as equipment failure or sudden weather changes. Emergency response teams are on standby during the entire lift operation, ready to act if necessary. Choosing the right cranes and lifting equipment is critical for the success of the operation. Given the enormous weight of the slurry reactors, each weighing 2,000 tons, specialized heavy lifting cranes are required. These cranes are typically crawler cranes, ring cranes, or even floating cranes, depending on the site layout and specific requirements of the lift. Crawler cranes are often used for their ability to move large loads across a site while maintaining stability. These cranes have an extensive lifting capacity and can be fitted with long booms to reach high elevations. However, if the site requires even more lifting power or if space is constrained, a ring crane may be deployed. Ring cranes are some of the most powerful cranes available, capable of lifting extreme loads with precision. In some cases, especially in offshore or near-shore installations, floating cranes mounted on barges are used to lift reactors from ships or docks and position them onto land-based foundations. In addition to the cranes, specialized rigging equipment is required to ensure the safe attachment and lifting of the reactors. High-strength slings, shackles, spreader beams, and lifting lugs must be custom designed to handle the immense weight and dimensions of the reactors. Every piece of equipment must be rigorously inspected and tested before the lift to ensure it is in perfect working condition. Once the planning phase is complete, the heavy lift equipment is mobilized and assembled at the site. This is a logistical challenge in itself, as the cranes and associated lifting equipment are too large to transport in one piece. Instead, they are disassembled into smaller components and transported to the site using heavy-duty trucks. Depending on the size and type of crane, it can take several days or even weeks to fully assemble the crane on-site. The assembly of the cranes requires a team of skilled engineers and operators who work together to ensure that the cranes are assembled correctly and calibrated to handle the weight of the reactors. This involves installing the boom, counterweights, and other critical components, as well as aligning the crane with the intended lifting path. During assembly, precise calculations are made to determine the crane's center of gravity and load distribution to ensure it remains stable during the lift. Once the cranes are assembled, they are calibrated to ensure that they can handle the specific weight and dimensions of the slurry reactors. This involves performing test lifts with smaller loads to verify the crane's stability, load capacity, and safety systems. Only once the crane has passed all necessary safety inspections is it cleared for the actual lift. Rigging is one of the most critical aspects of the lifting operation. Given the weight and size of the slurry reactors, the rigging must be perfectly designed and executed to prevent any imbalances or shifting during the lift. The rigging system typically consists of multiple high-strength slings, which are attached to specially designed lifting points on the reactors. These lifting points are reinforced to ensure they can handle the stresses imposed by the lift. Before the actual lift, load testing is performed to ensure that the rigging system is capable of safely handling the reactors. This involves attaching a test load to the rigging and lifting it to simulate the actual lift. The test load is usually a significant percentage of the reactor's weight, allowing the team to verify that the rigging system is functioning correctly and that the crane is capable of handling the load. With all preparations in place, the lift itself begins. This phase requires precision, coordination, and constant communication between the crane operators, rigging team, and safety personnel. Controlled liftoff. The slurry reactors are initially lifted off the ground at a slow, controlled pace. This allows the team to monitor the load and make any necessary adjustments to the rigging or crane alignment. Real-time monitoring systems are used to track the weight distribution and ensure that the reactors remain level during the lift. Even a slight imbalance can put dangerous stresses on the reactor shell, the rigging, and the crane itself. Multiple sensors are employed to monitor critical parameters, such as wind speed, load weight, and the angle of the crane's booms. This data is continuously fed to the crane operators, allowing them to make adjustments as needed. Additionally, spotters on the ground visually monitor the lift to ensure that the reactors are being lifted evenly and safely. Synchronization of cranes. In many cases, 2 or more cranes are used to lift the reactors simultaneously, especially when the reactors are too large or heavy for a single crane to handle. This requires precise synchronization between the cranes to ensure that the load is lifted evenly. If one crane lifts faster than the other, it can cause the reactor to tilt or shift, which could lead to catastrophic failure. To ensure proper synchronization, the cranes are often equipped with computerized control systems that allow them to operate in tandem. The crane operators are in constant communication with each other and with the rigging team to coordinate their movements and ensure that the lift proceeds smoothly. Final placement on foundations. Once the reactors have been lifted to the required height, they are carefully maneuvered into position above their foundations. This is often the most critical and delicate part of the operation, as the reactors must be lowered into place with extreme precision. Even a slight misalignment can cause significant problems during installation, so laser alignment systems and other precision tools are used to guide the reactors into place. The foundations themselves are designed to handle the weight of the reactors, as well as the dynamic loads that will be imposed during operation. They are typically constructed from reinforced concrete, with anchor bolts or welded plates used to secure the reactors in place. Once the reactors have been successfully lifted and positioned on their foundations, the installation process begins. This involves securing the reactors to the foundations, connecting them to the plant's auxiliary systems, and performing all necessary checks and tests to ensure that they are ready for operation. Securing the reactors. The reactors are typically secured to the foundations using a combination of bolting, welding, and grouting. This ensures that the reactors remain stable and secure during operation, even when subjected to extreme temperatures, pressures, and dynamic loads. The anchor bolts are carefully torqued to the specified levels, and the welds are inspected to ensure they meet all relevant safety and quality standards. Piping, electrical, and control system integration. The slurry reactors are then connected to the plant's piping systems, which transport raw materials, catalysts, and other chemicals into and out of the reactors. This involves precise alignment and welding of the pipes to ensure there are no leaks or weak points in the system. In addition to the piping, the reactors must be connected to the plant's electrical and control systems. This includes installing sensors, instruments, and control valves that monitor and regulate the reactor's internal conditions, such as temperature, pressure, and flow rates. These systems are critical for ensuring that the reactors operate within safe and optimal parameters, so their installation is carried out with the utmost care. The final phase of the project is commissioning and testing. This involves performing a series of tests to ensure that the reactors and all associated systems are functioning as expected. Pressure tests, leak tests, and operational tests are conducted to verify that the reactors can handle the specified loads and conditions without any issues. Once all tests have been successfully completed, the reactors are ready to begin full-scale operation, playing a key role in the plant's production process. The lifting and setting up of two 2,000-ton slurry reactors in chemical processing plants is a complex, multi-phase operation that requires meticulous planning, precision execution, and collaboration between multiple teams. Every aspect of the project, from site analysis and equipment mobilization to the final lift and installation, is designed to ensure the safe and successful handling of these massive and critical reactors. Given their essential role in industries such as petrochemicals, oil and gas, and fertilizer production, slurry reactors are among the most valuable and complex pieces of equipment in a chemical plant. Their successful installation is a testament to the engineering, logistical, and project management expertise required to handle such a challenging and high-stakes operation.